Hello everyone. The last 5 consecutive videos we have been deriving the theory for this classical plates. In this video, let us take one example to see the application of that rather long theory. So the example that we'll be taking up is this rather simple looking geometry where we'll be considering a circular plate which is subjected to a uniformly distributed load represented by this Q here, and which has a clamped boundary all around. It's a clamped periphery. Okay, so what I'm going to do is go back to the previous page where I stopped the previous video and copy the governing equations and boundary conditions in all their generality and try to see. So these are the governing equations and boundary conditions present, which we had obtained at the end of the last video, at the end of the long derivations. Let me copy this and paste it here, and let's see how this can be specialized to the present case of the circular plate. So first and foremost, what we have to note is that this particular formulation is presented in terms of the Sn coordinate system. However, a natural coordinate system of choice for this circular plate is of course the r theta coordinate system, that is the polar coordinate system, and we know or we can easily understand that here the n variable that will correspond to the r variable, and the s variable which is along the periphery that will correspond to r theta. So I believe this particular mapping which I have just written will not be difficult for anyone to understand. All right, another important very important point which considerably simplifies or massively simplifies rather our problem or problem solution is to notice that this is a uniformly distributed load. It's a perfectly clamped boundary all around, which makes this particular problem to be perfectly axis symmetric. It is extremely important to note this. It's an axis symmetric problem. And as we have seen a number of times earlier, especially during our course on applied elasticity, that such considerations of axis symmetry can significantly reduce the complexity of the equations at hand. For example, this equation which involves the biharmonic of the W deflection, that is considerably simplified in the presence of this axis symmetric condition. All right, now what about the boundary conditions? Okay, so we'll come to those governing equations and the solutions of that. You see, even though this is kind of the simplest problem which you could possibly tackle with classical plate theory, even then it does have its own challenges. So it is not that that we have successfully derived this very general theory. All that you have to do is simply plug in the various formula here, and we can directly arrive at the solution. You still need to understand the physical insights necessary for solving this problem in order to go ahead. Okay, so what are those things? First and foremost, we have to note which of these boundary conditions are applicable. Now that is one of the easiest questions, at least physically speaking, because we note that when you have a clamped periphery, all around the periphery, you are sure that the deflection has to be equal to 0. So from this condition, we know that W is specified all around the periphery. So if this circular plate has a radius of capital R, so we can immediately say that at R equal to capital R, W is equal to 0. Next, we also know that because this is a clamped periphery, the slope there will also be 0. The slope there being 0 means that it is this condition, the del W del N, which is specified, or it is 0. So not only this W is equal to 0 here, but we also have that del W del N, which is equivalent to del W del R, because you note that this N variable, it maps to R, that is equal to 0 all along the periphery. Now this certainly makes us happy, okay, that we have successfully modeled the given boundary condition, this clamped boundary condition, in terms of these boundary conditions that came about as a result of our long derivation of the classical plate theory. But there is a point of concern here, and that concern is, you see, if we write down this governing equation, okay, if we write down this governing equation, it is a fourth order equation, okay, no matter what form it takes, no matter what simplifications are available to us as a result of this axisymmetry, it is still a fourth order differential equation. Now that fourth order differential equation can be solved completely only if we have four boundary conditions, or four conditions to solve for the unknown constants. But here we have written only two conditions, okay. So what is missing here? So we have to understand that some conditions need to be specified at r equal to 0 also, okay. And what is it that motivates us to think specifically about the point r equal to 0? So we can understand that motivation only if we take up this governing equation and try to see its form. Well, it's like this. Our governing equation is this, okay, and we wish to write this biharmonic of W in terms of the of this r and r theta r and theta variables. But at the same time, you note that all derivatives with respect to theta, they will be 0 because of this axisymmetric condition. So anything which involves the del theta, or perhaps even del theta square, all those things will be 0. Now we also know that this operator, biharmonic operator, this can be equivalently written as the Laplacian of the Laplacian. And what is this Laplacian? So if we refer back to our discussions of applied elasticity, we'll see that this Laplacian, it came about as 1 by r ddr of r, if we write this W here, it's like this, okay. So we'll have to do this del square of W, and this should be quite familiar to you if you go back to the notes of applied elasticity, where we dealt with the biharmonic not of the W but of the eddy stress function back then, okay. So in terms of the mathematical form that it takes, it is absolutely the same. Now if we I mean, no matter what that is specific form is, you understand that it is involving this derivatives with respect to r. And what is the domain of this r? This r is going from 0 to capital R, okay. You understand here that our r here, it goes from 0 to capital R. So we already have specified, so we have our governing equation in terms of the derivatives of r. So that is our independent variable, and that independent variable is going from 0 to r, and we have already specified boundary conditions at small r equal to capital R. So all that we have to write, or what is missing from our framework, is the condition which should be written for r equal to 0, that is at the center of the plate. And that is the motivation here for considering some conditions which could be written at the center of the plate, that is at r equal to 0. Question is, what are those conditions? Well, uh, think about it. Okay, so can we directly say that at r equal to 0, uh, we know w? Can we say that? Well, certainly not. We cannot say that w is going to be 0. In fact, if you just think about this physical problem, you will realize that what is actually going to happen is that at r equal to 0, w is actually going to take the maximum value. Okay, but one thing is sure, that w at r equal to 0 should be a finite value. It may take on a maximum value, but it should be a finite value. And it is that condition of finiteness of w which will be actually helpful to us. Why we are specifically seeking this finiteness will be clear to us once we have the solution form for this del for w equal to q, and we'll look at that. The other condition which we'll again look at is, so we have three conditions in our hand now. The fourth condition that we are going to use is the fact that the moment uh, that has to be finite there also. Okay, so why again we are talking about the moment? That again will be clear to us once we have the solution form for this w. So the first thing that we have to do going forward is to seek a solution form for this d delta for w is equal to q equation, considering these things. Okay, so I have this del square w is equal to q, and that will be written like 1 by r ddr r ddr. So now I'm going to repeat this Laplacian again. You see, whatever is present within this curly bracket here, that is the Laplacian of w, and whatever is present outside, that is the outside Laplacian operator. So that is this Laplacian, and inside this curly bracket I have written this del square w. Okay, so we have to solve this, and let us not forget that we do have this d also present, and forgive me, this should be at 4. So there is a d present here. Now what we are going to do is to set q, which is a given constant, divided by d, which is another constant, that as a special value 64 beta. Now this seems like a rather mischievous trick, and it is a little bit mischievous in the sense, but it's very clever in the sense that if you keep on doing this integration, which you'll have to do eventually, because of this number of integrations, you will keep on obtaining various denominators as the integrations pile up, and in order to not have ugly fractions at the end, this kind of a 64 comes in rather handy. You can absolutely put this as just a constant k or some beta, it doesn't matter, but if you take the 64 here, ultimately those the rather large numbers in the denominator, they cancel out. Okay, and this is actually a trick which is present in the book Elasticity by Landau and Lifshitz, that famous series, which is part of that book is part of the famous series on theoretical physics. It's famous the world over, so we'll be referring to some of the examples from there. Okay, so if you do this and proceed, okay, if you keep on doing the integrations, and I encourage you to do that by with your own hand at least once in your life, or if you're feeling a little bit lazy, you can take access to symbolic Python in Jupyter Notebook. Whatever way you do it once, so ultimately what you will be obtaining for the solution form of W, please note that this is not the final solution. You will be obtaining it like this: beta r to the power 4 plus a r square ln r plus b ln r plus c r square d. Okay, and please note that I have not played any special trick to directly go from here to here. I have actually done this solution myself beforehand, and I'm just copying it and writing it here. But I encourage you to please do it. Okay, so please arrive at this solution form yourself. I'm not doing it. I'm not investing any time on this because it just involves some calculus and algebra, which most of you are expert at. Rather, I'd like to invest the time present in this video to actually do some serious discussions associated with the physical or the geometrical conditions associated with this problem. Okay, so you see, now that we have the solution form, I'll copy this in the next page. You see, this form, it contains the logarithmic terms. It has a r square ln r. It also has an ln r. Okay, so the discussion that we have to do with respect to this W is finite is reminiscent of things which we did in our undergraduate days in our courses on heat transfer, those heat conduction problems, and also those kinds of finite conditions associated with the finiteness of the solution. Those were also applicable when dealing with Poisson flows. Some people say it like Poisson flows. Anyway, so back in fluid mechanics and as well as in heat transfer, those were some of the places where we had, even in our undergraduate days, utilized the condition of the finiteness of the solution to impose certain restrictions on these constants. Now, please note that immediately by saying that at r equal to 0, the solution should be finite, we require that b should be equal to 0. Okay, so at r equal to 0, W should be finite. This is what we say. This is the first condition we actually impose. So this itself acts like a boundary condition. At r equal to 0, W should be finite, and this implies that B must be 0. From this term, okay, B ln r. Please note that I also have this logarithmic term here, but it is multiplied by this r square. Now, you note that as r tends to 0, although the ln r term that tends to minus infinity, which is something which would make the W to be infinite, but at the same time we have this r square term. So this r square term that itself tends to 0. So we have the form as r tends to 0 as 0 times infinity, or it can be written like a 0 divided by 0 form, or a infinity by infinity form. So there is some hope perhaps that this term could perhaps contribute potentially to some finite value of W. We are not sure. Okay, so we'll have to seek another condition to see what is the fate of this A. And the condition which will impose there is to say that the moment at the center, that also needs to be finite. Okay. Now let's see. There is a challenge here actually. Okay, so it is one thing to say that the moment is 0, but what is the form of the moment itself? That we don't know. That we have not derived. So And let me go to the next page and just write down the expression of the moment. And when I say the moment, I mean this moment. So this basically corresponds to Mn. Okay, what we had obtained as Mn, this is the part associated with that. So this is the Mr associated or correspond to this, that Mn. Now this Mr, it takes the form this. Let me write that down and then I'll have a discussion. D square W dr square plus nu by r dw dr, where you please note that this nu is the Poisson's ratio, and this nu is the same thing which is actually present within the definition of the coefficient d itself. Okay, now how did we arrive at this? Well, this is actually part of or it is actually one of the problems in the problem sheet number 3. So people who are watching this video and who are enrolled in this course of advanced mechanics of solids will have an opportunity to do this problem officially. I'll post a link to the problem sheet in the description of this video also, so people who are not enrolled in this course may take a look, and for people who are enrolled in this course, if you have any doubts, we can always discuss it in the live session. But let me just give a hint here that this Mr, it can be obtained from the general expression of Mn. That Mn can be represented in terms of the cos theta and sin theta, but there is a direct route of going from the xy coordinate system to the r, and that we have already we know the recipe of doing that from our studies in applied elasticity in the previous semester. Again, for the reference of those who are not enrolled in this course and watching this video, there's a separate playlist on applied elasticity. I'll put the link of that in the description of this video also. Detailed discussions in going from the xy coordinate system to the r theta coordinate system were done in the course on applied elasticity. Rather easy to do once we know what to do using symbolic Python. So I will not invest any more time beyond this hints. Rather, I'll go ahead and try to utilize this this information here. Okay. Now, what I'll do is, let me paste this thing, paste the solution form. Now, this much I will do. So, dw dr, that is 4 beta r cube plus twice ar ln r plus ar plus b by r. But you note that this b has been already set to 0, so we might not as well consider it. And then we have this twice cr, then this is a constant. Next, for d square w dr square, we have 12 beta r square plus twice a ln r plus twice a plus a minus b by r square, and of course this plus twice c. So I might as well cancel these terms. So b is 0. So I have to go back to this expression of Mr and do this thing actually. Okay, now what I'll do is I'll play a little trick here, and instead of writing this within the whole bracket, it's only going to clutter it up. I'll do this Mr divided by t. Okay, so I'm free to write these terms nicely. This is 4 beta r 4 beta r cube plus twice a r pardon me, I should be first writing this So this is plus 3a plus twice c. So that is my d square w dr square plus I need to write this nu by r. So I'll do that operation in one shot. I'll divide throughout by r for this expression. That will give me 4 beta r square plus twice a ln r plus a plus twice c. Okay, so this is basically my mr expression, and I need, so what we had said was that at r equal to 0, mr should be finite. Now you see what is the benefit. Okay, so it's like a posteriori realization of the benefit of this, of taking this thing. So if we say that mr should be finite, we can actually impose a condition on this a, because you see, just like previously, the term involving the b was left with just the lnr term, had the lnr term. So now also this a has this coefficient lnr. You forget about the rest of it. Okay, if you consider this term here, this here is a, and you note here the other lnr term that also has the a in front of it. You can't say anything about this given Poisson's ratio. 2 is just 2. So the implication here is that a must be 0, because if a is not 0, then this ln r here and this ln r here is going to make this mr to be tending to infinity. Okay, and that is not acceptable. So a must be 0. So we have a situation which is considerably simplified. W here now is we don't have to deal with this b term, we don't have to deal with this a term. So therefore our W is beta r to the power 4 plus c r square plus d. Okay, so let me copy this and go to the next page. Now we can utilize the boundary conditions which we had written down at all. Sorry about that. We can utilize the boundary conditions which we had written at r equal to capital R. Okay, so at r equal to R, we have W is equal to 0, which implies beta r to the power 4 plus c r square plus d is equal to 0, and also at r equal to R, we had dw dr is equal to 0. Let's not forget that we have already obtained the expression for dw dr in this page, so I can just utilize it from here. You also note that this a is 0, this a is 0, and here the only thing, and this small r is of course can be replaced by this capital R. So what we have for C is that C is equal to minus twice beta r square, and the moment we have the C, we can go back to this equation and write it. So C can be replaced by this twice beta r square, so this is twice beta r to the power 4 minus beta r to the power 4, so that is just beta r to the power 4. So finally what we have is W is equal to beta small r to the power 4 plus, for C what we are going to do is write this thing twice beta capital R square. Let's not forget the small r square which is present here, and for this small d I have this beta r to the power 4. And please note that this is a very nice form because this is simply r square minus r square whole square. Okay, you can check, you can take beta common. This is r4 minus twice small r square capital R square plus r4, so that is just this form. All right, so this is our solution, and if you just wish to write this, this is q by d, and so this comes with a 64. Let's not forget that. So this is our solution. Okay, nice clean solution, and as expected, this takes on a very nice axisymmetric form also, and you can actually check that the W is going to be maximum at r equal to 0. Okay, now even with the simplest of setup, you see that we had to contend with at least a couple of difficulties, and later on when we address problems involving the simply supported condition at the periphery, the things will be slightly more complicated. Okay, but nevertheless it is possible to obtain solutions uh, for those situations also. All right, on that note I will end this video. Thank you very much.